Hello students. Today's we will learn about number system. So what are numbers? What are numbers? We will know what are numbers. Okay. And why do we use them, where they have advantage in our daily life. So let's start. We have different types of numbers. Basically numbers are just uh, quantities which helps us to remember the uh, quantities of objects. Okay, so numbers are just entities which are required to give quantity or give some measurement to object. Okay, so let's jump into our topic. So first we see the types of or the classifications of numbers. What are the different types of numbers? If you recall, the number there we first learned about natural numbers. So the natural numbers are counting numbers. One can say the natural numbers are counting numbers, which means that the numbers which helps us in counting, say 1, 2, 3, 4, 5, etc. Okay. And this set is denoted by n. Okay, the natural number set is denoted by n and the elements are 1, 2, 3, 4, 5, 6 and so on. Okay, now second classification is the whole numbers. The whole numbers okay, the whole numbers are just nothing. The numbers consisting of natural number plus an extra entity called 0. So this is the extra one. Okay, so the whole number is denoted by W, and the whole number system set is equals to the natural numbers plus union. Union means I am adding one extra. This is the symbol for union. Symbol for union meaning adding of an element. Okay, so what is the element? The 0 element. Okay, the 0 element. So whole numbers is a set denoted by W, which consists of 0, 1, 2, 3, 4, 5, 6 and so on. Okay, now the third classification, the third uh, type is integers. So integer consists of both the natural numbers, whole numbers and the negative of natural numbers. Here are the negative natural numbers, the -1, the -2, the -3 and so on till minus infinity, here plus infinity to it must be minus infinity. Okay, or 0, and this is the system for the whole numbers. Okay, so 0, 1, 2, 3 are all whole numbers, or one can say this is the set for natural numbers. That is 1, 2, 3 till. Okay, let's move. Now the rational numbers. So what are rational numbers? We have learned about the natural numbers. Natural numbers denoted by n starting with 1, and the next number is added 1 added to 1, which is 2. Now added again we add 1, which is 3 till so on till to infinity. Now whole numbers are starting from 0, and then now comes the natural numbers 1, 2, 3 till infinity. And integers denoted by z is equals to we start with, here the center point is 0, and to the right side we having natural numbers 1, 2, 3 till infinity, and to the left of 0 we have -1, -2 till minus infinity. this is the set of integers. Now comes to the rational numbers. The rational numbers are of the form p upon q. P upon q form, where p and q are integers. That is, p and q are belonging to the set of integers. So the set of integers here. So p and q can be from among these numbers, except there is one condition, that q must not equal to be 0. So we choose p and q such that q is not equal to 0. So for example, the 2 upon 3 is our rational number, 37 upon 15 is rational number, minus 17 upon 19 is also an rational number. Now, all if you see that natural number system, the natural number set is starting from 1, and the next element is adding 1 to 1. Now adding 1 again to 2, which gives us 3 till infinity, and the whole number set is starting from 0, then adding 1, then again adding 1, we get 2, 3 and so on till infinity. If you see that these numbers are natural numbers, so we can say that all natural numbers are whole numbers. We say all natural numbers are, all natural numbers are whole numbers. Okay, so all natural numbers are whole numbers. Clear? So note. Now all natural numbers, whole numbers and integer are rational number. Why all natural, whole numbers and integers are natural number? So first comes to the natural number. We know that all natural numbers are whole numbers. Okay, so if we somehow show that whole numbers are rational numbers, then we can easily say that natural numbers are also whole numbers, because all natural numbers are whole numbers. Similarly, if you see that natural number set is starting from 1, then 2 till infinity, and then whole number set is starting from 0, 1, 2 till infinity, and then integers starting from we have the center at 0, then 1, then 2, then infinity, and to the left side minus 1, minus 2 till minus infinity. If I try to make a space, that is, here is the circle where here is a bag which contains n, that is natural numbers, then we see that W is the bigger bag because it contains an extra element which is 0. Now easily we can see these are from this, so we can easily see that the bag of Z is much bigger than the bags of N and W. So okay, so if we somehow show that all integers are rational, then we can say that all whole and natural numbers are also rationals. Clear? Now, so how we can say that integers are rational? So showing or giving reason for this, the integers are rational, we can conclude that the all natural numbers and whole numbers are also rationals. So integers, we know what are integers. Integers are 0, 1, 2 till infinity, and minus 1, minus 2 till minus infinity. Okay, to integers to be like rationals, it must have the form P upon Q, where Q is not equal to 0. Always remember that. Okay, so take any integer. Let's suppose 1. Here 1 is our integer. Yes, so I can write 1 is 1 upon 1. Yes, I can write. So it is of the form P upon Q, where P is 1 and Q is also 1. So it is of the form P upon Q and Q is not 0. So I can say that 1 is a rational number. So similarly, in the similar manner, I can say I can take any integer, I can take any number, any integer number, say minus 100, and I can write it as 100 divided by 1 or 100 upon 1 minus 100 upon 1. So here P is equals to minus 100 and Q is equals to 1, where Q is not equal to 0. So I can easily write any integer, I can write any integer number, I can write any integer number in the P upon Q form, where integer number is equals to integer number upon 1, where P will always be the given integer number and Q always be 1, which is not equal to 0. So it satisfies all the conditions for the rational number. So every integer, is a rational. Clear? So from this we can say all whole numbers are also rational, and all natural numbers are also rational. Now the second point, the rational numbers include all integers. Yes, I have already told you. Okay, without any decimal part to it. Okay, now terminating fractions in which the decimal part terminating, example. So we are talking about fractions. Okay, so fractions, we know fractions have the form P upon Q. Okay, and Q is not equal to 0. So rational are of the form fractions, where P upon Q, where Q is not equal to 0. And the fractions are divided into various types. Okay, so we will discuss them. Now here we are talking about terminating fractions. So terminating fractions, what do we mean by that? Terminating fractions means, let's say we have 1 upon 2. What the decimal form of it is 0.5. So after we have this this type of form, so it is terminated. We don't have any other number after right side of the 5. Okay, so it is terminated or the terminated number. Okay, terminated. Clear? And if you talk about non-terminated numbers like 1 by 3. So 1 by 3 is what? 1 by 3 is 0.999, sorry, 0.333. It goes forever. 3333. Okay, so it is not terminating. So clear? So terminating numbers meaning the decimal form of the fraction must be stopped after some points. Okay, so here like 0.75, so we are restricted to only 2 decimal points, 7 and 5. Then here minus 0.02, the the number is terminated. Okay, and non-terminating numbers but recurring decimals. So this means for example, I have already shown you here this is non-terminating, but if you give some thought that it is repeating, the numbers 333 is forever repeating, so it is non-terminating plus repeating. Okay, clear? So the rational numbers are also can be defined as like this. So the rational numbers are in the P upon Q form, where Q is not 0. If we see their decimal form, then the decimal form must be terminating or must be non-terminating but recurring. So clear? Yes. Okay, let's move further. Now fractions, we come to the fractions, the types of fractions. First we see the common fraction. The common fraction meaning is the fraction in which the numerator and the denominator both are integers. For example, 1 upon 2 is a common fraction, 3 upon 4 is also a common fraction, 0.1, 0.5 upon 0.2 is not a common fraction. The numerator and denominator must be integers. Now decimal fractions meaning the fractions whose denominator is 10 or any power of 10. For example, 1 by 10 is decimal fraction, and 2 by 100, which is equal to by 10 raised to the power 2, which is also a power of 10. So it is a decimal fraction. Now comes to the proper fraction. Proper fraction meaning the numerator upon denominator. So the numerator part is strictly less than the denominator part. For example, 3 upon 5. So 3 upon 5 is our proper fractions. Let's take another example, say 4 upon 100 is also 4 upon 100 is also our another improper fraction example. Okay, clear? Let's move. Now we see the improper fraction. Here in improper fraction, the numerator is strictly greater than the denominator. For example, 5 upon 3. So the let's take another example, say 100 by 1 is also improper fractions. Okay, now we see the mixed fraction. In mixed fraction, it consists of integral as well as the fractional part, which is like this. So the meaning of this is equals to that the 3 plus 2 by 7, that is 3 whole, we read it as like 3 whole 2 by 7. Okay, here 3 plus 2 by 7. In another meaning of this is this. Now the compound fraction. In compound fraction is the fraction whose numerator and denominator themselves are fractions. That is, the numerator is also a fraction, some sort of fraction, and denominator is also some sort of a fraction. Okay, let's move. Now let's see the irrational numbers. So irrational numbers, what are those irrational numbers? Now we have seen the rational numbers. The rational numbers are of the form P upon Q, where Q is non-zero, not equal to 0, or one can say in decimal form, the rational numbers are terminating numbers or non-terminating but repeating. Okay, so example, 1 by 5 is rational. 1 by now let's take a decimal form. So 0.25 is also rational. 0.2222, the 2 is repeating forever, is also rational. And now let's take an example of not a rational number. Okay, so not rational example is 0.10, then 100, then 1000, then 10000. So it is an example of not rational number. So it is not repeating any pattern or not terminating. So it is not a rational number. Okay, so the all real numbers which are not rationals are called irrational numbers. So previously I gave an example. So it is an example of irrational numbers. Okay, clear? Irrational numbers. Let's see another examples. So root 2, cube root of 4, 2 plus root 3, root of 2 plus root 3. Okay, so all these are of examples of irrational numbers. One can say that the irrational numbers are non-recurring. That means non-repeating and non-terminating. Okay, non-repeating and non-terminating. And these type of decimal numbers are called irrational numbers. Okay, clear? Let's move. Now real numbers. So we have talked about rationals and irrationals. Okay, so rationals and irrationals. So combination of all those numbers, rational and irrational, meaning that if I have a bag and I put rationals in the bag and irrationals also in the bag, then this whole bag we called it as the real numbers. So real numbers are just nothing. It is the combinations, or we can, or more precisely say, it is the collection of all rationals and irrational numbers. Okay, so real numbers are collections of all rationals and irrationals. And irrationals. Okay, and numbers which can represent actual physical quantities in meaningful ways are known as real numbers. Nothing new to that. Okay, now we have real numbers. You understood real numbers. Real numbers consist, or it is a collection of rationals and irrationals. I have already told you the definitions for, or the representations of rationals and irrational numbers, how they looks in decimal form or in fractional forms. We talked about the fractions, the different types of fractions, the integers. We talked about integers, the whole numbers, and the natural numbers. Okay, so now we have come to the real numbers. Now how we gonna represent them? So we have a number line. Okay, so we have just a imagination of there is nothing like number line existed physically, but we imagination we assume that there is a number line where we can put our numbers onto it. So this number line we say real number line. Okay, or the number line, because real number line, because the number line is for the reals. Okay, so first we have a line, we put our origin, and where we say here are zero number. Okay, it is a whole number or integer or a rational number also. Okay, right side to it is positive real number, positive reals or real numbers. Here left side to the 0 is negative numbers, negative real numbers. And 0 is neither positive or negative. Always remember, 0 is neither considered as to be positive or negative. Okay, now jump to our lecture. So now we jump to the prime numbers. So what are prime numbers now? Prime numbers are all natural numbers. Okay, we know prime numbers are natural numbers that have, so the conditions for the prime numbers is that have 1 and itself as their factors, which means that if p is a prime number, p is prime, if p is prime, then only 1 and p divides p. P means this p. Clear? If this holds, then p is a prime. Okay. For example, if you say is 2 prime, let's see, 1 divides 2, yes. 2 divides 2, yes. So 2 is prime. Okay. So 2 is prime. 2 is prime. Now what about 4? So let's see the factors. 1 divides 4, yes. 2 divides 4, yes. 4 divides 4, yes. So we see that we have 3 factors. Okay. Apart from this, we have this 2 extra factor. This 2, number 2 extra factor. So we have 3 factors. But prime have only 2 factors, namely 1 and itself. Okay, so 4 not prime. I hope the definition is clear. So what are prime numbers? Okay, so prime numbers are exactly divisible by 1 and themselves only. So prime numbers have only 2 factors, 1 and itself. So for example, 2 is our prime, 3, 5, 7, 11, 13, 17. All these numbers are primes. Okay. Okay, let's move the composite number. Now, what are composite numbers? Composite numbers are those numbers which are not primes. That means the numbers having more than 2 factors. For example, 4 is composite, 6 is composite, and so on. So 4, 6, 8, 9, 10, all of these numbers are composite. There's one thing to remember. That number 1, we consider it as neither prime number nor composite number. Okay, we always take 1 is neither a prime number nor a composite number. Okay, I hope the things are clear. Now co-prime numbers. Whenever we talk about co-primes, co-prime meaning the first we always in co-prime numbers, we always took pairs of numbers. So we have a number A and there's another number B, then A and B. If we say the A and B are co-prime, A and B are co-prime numbers, then we are talking about the HCF of them. So HCF of A and B is equals to 1, then A and B are co-primes. Then we say A and B are co-primes. Clear? Okay. So whenever we talk about the co-primes, we mainly talk about the pairs of two numbers. Okay. And the HCF of those two numbers must be equal to 1. Okay. 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 Now let's take another example. Say, is 2 and 3 are co-primes? Yes, because the HCF of 2 and 3 is equals to 1. Is 2 and 4 are co-primes? No, because the HCF is 2. Clear? Okay, now let's talk about the even numbers. So even numbers are those numbers which are divisible by 2. So take any numbers, if it is divisible by 2, it is even. If it is not divisible by 2, we say that number is an odd number. Okay, clear? It is quite simple definition for odd and even numbers. If it is divisible by 2, it is even. It is not divisible by 2, it is odd number. Okay. Now talk about the imaginary numbers. So imaginary numbers are just nothing. If A is any imaginary number, then the square of that number must be some negative number. So all the numbers whose square is negative is called imaginary numbers. For example, I. We denote iota, I by iota. We define I square is equals to minus V. Okay, so we already defined iota I square is equals to 1. Okay, so 3i, so squaring 3i, so 3i square is equals to 3 square I square, and we know 3 square is 9, I square is minus 1, so minus 9. So square of a number is negative number, so it is an imaginary number. Same with 4i, etc. Okay, so here we already defined I is equals to root minus 1, or I square is equals to minus 1. Okay, now complex numbers. The combined form of real and imaginary numbers is known as complex numbers. So complex numbers are of the form A plus IB, where A and B are from real numbers, the bag of reals. Okay, where A or B can be rational or irrational, and I is already defined as the imaginary number, or I is already defined is equals to be root of minus 1. Okay, so any number of this form A plus IB is complex number. For example, 3 plus 5i is also complex number, where 3 is a positive real number and 5 is also positive real number, and I is iota, that is I is root minus I. Okay. Now identification of prime number. How do we identify if a given number is prime or not? First, approximate a square root of given number. Okay, so let's say I have given 101. Say, is it prime or not? Prime or not? Prime or not? So 101. So first step is to approximate the square root. So square root of 101 is something like 10, around 10 something. 10 point. Okay. we have to approximate it. So I come to this, that 10. Okay, now divide the given number by prime numbers less than approximate square root. So the approximated square root, approximated something, okay, 10 point something. So approximated square root is 10 point something. So let's divide the original number 101. Okay, let's divide the original number by the prime numbers less than or equal to the square root. So the prime numbers less than 10. So first we have to list out the prime numbers less than 10. So 2, 3, 5, 7, okay, are the prime numbers less than 10. So if is to divide, completely divide. So divide meaning here is completely divides. Does 2 divides 101 completely? No, because it is not even number. 3 divides? No. Is 5 divides? No. Does 7 divides? Does 7 divides 101? Let's see. If you are not getting, let's just do a long division method. So 7 is 3. No. So one can easily see that the 7 also doesn't divide 101 exactly. Okay. So now if this happens, then the given number is not divisible by any of these primes, then the number is prime numbers. If so, we saw that none of the primes from the list we have taken out divides the 101, then we can say 101 is prime. 101 is prime number. Okay, clear? I hope the steps are clear. Let's take another example. So 571, is it a prime? Say first take approximated root. We know 25 times 25 is equals to 625. Okay, we know 25 times 25 is 625. So we can easily say the root of this is must be equal some less than 25. Okay, or if you now let's do for 24 times 24, which is equals to 576. So yes, the approximated root will equals to be like 24 something. Okay, so now now the approximated root is 24 something or 25 around something. Okay, now make out the list of prime numbers less than 24. Let's make 2, 3, 5, 7, 11, 13, okay, 17, 19, 23. Okay, so this is our list. So now let's see which of the numbers divide our original number. Okay, does 2 divides? No, because it is not even number. Okay, does 3 divides? If 3 divides any number, then the sum of the digits of the number must be divisible by 3. So 5 plus 1 is 6 plus 7 is 13. So 3 doesn't divide 571. Now check for 5. 5 divides? No. If 5 divides any number, then the unit digit or this digit, the first or the unit digit, either 1 or either 5 or 0. So 5 here, the digit is given to us is equals to 1. So 5 doesn't divide 571. Okay, now the 7 divides. The 7 divides 571. Let's check. Now we'll try to figure out by long division method. Okay, so it will take a time, but the number given to us is not lengthy. It's just 3-digit number. Okay, so 56 1 1. So it also doesn't divide completely. Okay, no. Now check for 11. 11, for 11 it doesn't divide it completely. We can easily see from the first step only. Okay, okay. Now for the 13. Okay, now for 13 we see that 3 times 39. Okay, 3 times 39 and 4 times 52. So it also, we can easily say it is also not divisible. Okay, 39 completely. Now let's check for 17. Okay, now let's check for 17. So for 17, 3 times is 51. It is also not giving us the complete division. So okay, now let's see for 19. Okay, let's see for 19. So 19, 3, 57. The remainder is no. This is also not going to work. Now the only number remaining is 23. So 23 times 2 is 46. 23 times 3 is 69. So 23 times 46. Okay, 46. And 11, we are left with 11. And if we see that this is also not going to work. So this is also not going to work. So none of the numbers from the list divides the number 571. So we say that it is a prime. Yes, it is a prime. Okay. So okay, 5 is not divisible by any of this. So 571 is a prime number. So thank you for this session. We will continue after this for the next time. So thank you having with me. Okay, thank you.